I will get started. Hey everyone, I am Jeremy, the CEO of RISC-0, and today I'm just going to be talking a little bit about sort of what you can do with RISC-0 and ZK proofs in general, and what kind of applications they have, a little bit. So first I want to give a little bit of background about what is RISC-0 and a little bit about zero-knowledge proofs. I figure most people know a bunch of that at this point, but just in case, talk about sort of where we are as of right now, which I want to release, and then go into some different use cases and sort of talk about what the sort of next steps are for everything. So, what is RISC-0? Well, let's start with the earlier question of what's the zero-knowledge proof. I think most people here probably are aware, but basically a zero-knowledge proof lets you show that something is true without telling everyone all the details. And most importantly, it's in such a way that anyone can check the results very rapidly. So even if I'm proving something very large and complicated, like this program compiled to this or whatever, I can check it very rapidly. So historically, programming ZKPs has involved this very complex translation of the thing you actually care about proving, like some chess position as checkmate, into a system of polynomial constraints over finite field elements, which is about as programmer friendly as it sounds. And I think that this has limited a lot of the application of ZKP because while it's super cool and very powerful, the development process for doing this translation is quite hard. And so the idea more recently with RISC-0 as well as some other people who've been working on this is this idea of a ZKVM, which is instead of making a arithmetic circuit that represents the thing you want to prove, instead you make an arithmetic circuit that represents a processor or a VM. And then now that your ZK proof can run this VM, you can now take ordinary code, translate that into a binary that the ZK VM can run, and then run that inside the ZK VM and result in a proof. The key thing about this is that what it means is that you now have the ability to write programs instead of circuits, and you can just write ordinary programs. And one of the key things that RISC-0 did when we were sort of the pioneers of this idea was to ask, well, why don't we make that VM something that actually looks like an existing real-world processor that's already out there? In our case, we chose the RISC-V processor because it's a very small, very simple processor, much less complex than an Intel processor or in the ARM or whatever that's in your phone. But it's also something that was already well supported by most languages, right? Like Rust already compiles down into RISC-V. And so by making that choice, we made it so that you could take ordinary programs like written in Rust and actually run them inside of zero-knowledge proof. So here's like the example of like the chess example. And what's cool about this is that because we picked something that there was already existing support for, what that means is that you get the entire ecosystem of the language. There was already a chess package in Rust, and you could just import it. And so not only do you not have to write it as a circuit, you don't have to write the rules of chess again, right? So I think that this is sort of opens up a lot of different opportunities. I think that one of the things is that, recently RISC-0 is now production ready. We've gotten to our ZKVM 1.0, which has a stable API for both generating proofs as well as the API that you see within the Rust. We've done the necessary work to cryptographically secure the setup ceremony, which is actually necessary only for the Ethereum proving part of it. The underlying proof system doesn't require trusted setup, but to get them small and efficient on Ethereum, we do. And then we've gotten basically verifier contracts on mainnets for a wide range of mainnets. And we have done a lot of work on security. We have had audits of the actual VM itself, the proof system, the RISC-V circuit, the method by which we put the proofs onto blockchain to verify. And we not only have we done audits, but we also have a very strong internal security process to make sure that not only do we have very careful review of anything for the next version, but just in general that we've got a really strong internal process. So at this point, we are representing as a company that if you go lock $100 million behind some smart contract secured by one of zero-knowledge proofs, we are saying yes, you should do that. And so I think that that's very important, and we've been really excited to get to this point for a long time, because while things have been basically usable for many, many, many months, getting to the point where we really feel like we're ready to tell people, go use this in production, it's a huge deal. And I think one of the things that's important too is our performance is really stellar. We are by far the fastest in terms of producing proofs of RISC-V execution. We're also much less expensive, both in the cloud and on super great hardware. We're at about 500 kilohertz of RISC-V execution on a single GPU. As just a concrete example, what these costs really mean is that if you wanted to prove an entire Ethereum block by, say, running the EVM inside of Ref, which is like a RISC, EVM library, running it and proving the correctness of an entire block costs less than $1. So I think that these costs start to become, which is a fraction of the gas fees, right? So the key thing is that because of these costs, it's now way cheaper to, in many cases, any problem of any significant size, it's way cheaper to prove it, to pay the cost to generate the zero-knowledge proof off-chain and then verify it on-chain than it is to just execute it on-chain, right? So this is one of the key scalability things that ZK allows. So I kind of wanted to talk about, we'll start with the scalability use cases, right? So obviously because of this and the ability to sort of move computation off-chain, we're seeing a lot of ZKL2s that are using our stuff, because they can just prove the state transitions in ZK. We're also, interestingly, there's also a lot of use cases for ZK even in optimistic systems. So typically people think things it's an optimistic thing or it's a ZK thing. But actually, one of the things is in an optimistic system, if someone falsely states, actually the new state is X, but it's really not X, then the process of proving that they got it wrong is this whole back and forth process that involves many steps, and leads to these very long windows that you have to wait to determine whether your thing was actually right. And with using ZK, you can say if someone detects fraud, they can, instead of going through this whole game of going back and forth, they say, that's fraud. Let me just make a zero-knowledge proof that given the previous state, the new state should be Y, and you said X, and they post that proof, and then the whole thing is done because you've basically just proven a single step. So we're talking people about that, and then also roll-ups, obviously, a similar idea, to L2s, and that you're proving the state transition function, with ZK. And another sort of way to use this sort of off-chain computing is this notion of sort of a ZK coprocessor. So the idea with this is that rather than having the state live off-chain like an L2, where the state for the L2 is somewhere else, in the case of a ZK coprocessor, your state is still on whatever chain you're running on. But rather than doing the compute on that chain, you simply do the proof about whatever you want to show as your update off-chain, but reading the on-chain state, and then you use that proof to then update your on-chain state. So you're just moving just the execution, just the computational part off-chain with this sort of ZK coprocessor model. Maybe some people working on things with that. I think this is actually an interesting, as the cost for verification continues to drop, and we'll get into working on some mechanisms for aggregation to get the cost for verification down to, we think we can get it under like 20K gas, amortizing. That you're going to see it's going to become increasingly silly to do much computing at all on the chain, and many, many, many use cases are going to be, let's just do the compute off-chain, and you're going to see just a lot of ZK verification on-chain. So I think privacy use cases are also really super important. One of the really interesting ones is you can actually, for example, do single sign-on with third-party off-chain companies in an on-chain context. And the way this works is that you go do your login with Google. Google will then sign this cryptographic document, and you can then verify that cryptographic document in ZK and post the proof that you verified it without revealing the things that are in the document. Which means you can also say, for example, I logged in with Google, and here's a hash of my, all of my identifying information, so you don't know who I am, and you know that I have a Google account, you know it's a unique one. Or you can say, actually my name begins with the letter J, or I'm over 18 if Google has metadata on that. And you can even use the sort of government sign-in mechanisms. Actually, speaking of which, passports also have similar cryptographic identifying information. So it's actually possible for you to generate a zero-knowledge proof that I hold a passport and I'm a U.S. citizen and I'm over 18. And here's a unique number that is unique to me, but is not related to anything that identifies me. So I think there's a lot of cool abilities to sort of bring some of these off-chain things onto the chain. And actually, this is another fun little demo that someone put together, which was this proof of accredited investorship, where again, the idea is that you show that you correctly got documents via TILS notary from the IRS, and then you redact everything that you don't want to be seen, and you generate a zero-knowledge proof that all the steps were done correctly, posted on chain, and now, yes, I have identified it as an accredited investor. So I think these kinds of identity use cases are going to become increasingly important. And in terms of other use cases, I think there's a lot of other ideas that people are working on that it would take me too long to talk about, but ZKML is obviously one, both for verifying inference, and also people are working on the training thing. I think from a performance perspective, it's still not there yet, but someday. ZK bridging, proving the execution of one chain to another chain to allow faster and error-free bridging. Gaming use cases, there's tons of use cases. Actually, there's an interesting this idea of the proof of exploit, which is this idea that you can show that, let's say there's a program, and I know that you shouldn't be able to do X, but I happen to know that there is an exploit in the program. There's something wrong with this smart contract. And if I give it this evil input, then I can convince it to do the thing it's not supposed to do. I can actually generate a zero-knowledge proof of me executing it and exploiting it with that input. And I can say, I have proof that I have broken this piece of software, but I don't have to tell you how I've broken it. I'm not exactly sure that this is a good thing to exist. It seems like a good way to market exploits, but anyway, it is a thing you can do. And then actually, I think that there's an interesting use case for. We're actually getting close to sort of working on getting RISC-C running inside of our zero-knowledge proof system. So you can in fact prove that this source code translates into this binary, or even as far as this GitHub commit, when I ran this huge build, produced this binary. And then you can actually sort of know that that this is a huge importance for supply chain sort of security concerns. And a lot of this stuff, by the way, goes way beyond sort of blockchain use cases. But I think that right now, obviously, that's the.
Any idea the cost of that?
Expensive. But when you think about it like this, compilation is on the order of hundreds of billions of cycles, but so maybe it costs but with the performance that people we're getting nowadays, maybe it costs $30 or something for compiling a non-trivial sized program. Yeah, and if it's something really big, but it's really important, like compiling the Linux kernel, for example, honestly, if it's $500 a compute to prove that you've compiled the Linux kernel right, once you've done that, you can reuse it infinitely and everyone can verify it without having to rebuild. So I think there are use cases where even if it's expensive, it may still be worthwhile, right? I think in terms of what's coming up next, we're working very hard on even more performance. I think in the last quarter we got almost a 3.5x across the board speed up, and we're continuing to work on that. I think we'll probably have another 2x at least this quarter. We're also working on accelerators, or I think SP1 calls them precompiles, but the idea that there are certain cryptographic operations that are not really super fast to run on RISC-V in a 32-bit processor. So instead, you basically add to the proof system the capacity to do these additional specialized circuits. So we're adding a bunch more of those, and we're also adding a mechanism for third parties to be able to add those. And then the most interesting thing is we're currently at the very have internal work that we haven't announced really yet. I'm just mentioning in a couple of talks on the network. So one of the questions is in these blockchain use cases, like let's say the co-processor use case, if you want to have someone prove it, the question is who's going to do the proof and send the result to the chain to be verified, and how do you do that in a way that is decentralized and has appropriate guarantees about censorship resistance and availability. So we're working on a mechanism for doing that. If you are interested in being either helping work on applications and making use of that, or one of the people who wants to run provers that are going to be generating the proofs on this network, scan this QR code and talk to our people. And yeah, this is me. That's some information about other things that our company has going on at ECC. And yeah.
I think you might want to go back.
Oh yeah, sure. Oh, yeah. Hold on, get the QR code there.
Thank you. How do you think about states? I guess you have the verifier on these layer 1, layer 2.
Yes.
And there's the different use cases. Presumably you don't have any opinions about how they manage their state.
That's right. And actually, like the big difference between say, the L2 use case and the coprocessor use case is the coprocessor use case, the state is all on the L1.
Yeah.
And it's really just making a statement about there is this state on this L1 on the L1 right now, and so X, Y, Z is true.
Yeah.
But in general, as we move toward the network, that we will provide multiple different options for managing state. We have actually another, for example, we have and we're also going to provide a lot more integration to make it easier for people to talk about state in other places. So for example, we have a Steel one, this library called Steel right now, that basically lets you run view calls on Ethereum state. So it'll generate a proof that if on block X of Ethereum I ran this view call, this is what I would get back. But yeah.
And you don't want to be opinionated on how the different people use RISC-0.
That's right. We're very much, our goal is we're going to support RISC-0. We're going to try to support the idea of making and verifying proofs on every chain. And not just our proof system, we'll actually have the ability to use our aggregation mechanism to aggregate other people's proof systems. We very much want to be sort of a neutral party. Our real goal is to help make it easier for people to use zero-knowledge proofs in as much of a seamless way as possible. We're working on a Solana verifier and all those kinds of things too, so yeah.
We have a few minutes for questions.
Go ahead.
I'd be really curious to know the heuristics you use to try and understand the underlying affordances with regard to scaling. So often when I'm trying to explain what makes ZK exciting to people outside of the space, I'm trying to reach for something which kind of feels a little bit like Moore's law.
So I think for one of the things I always use when I'm trying to explain how massively the impact of scaling on ZK is on blockchain space is the idea that if you think about running something on Ethereum, every validator, or at least every full node, has to fully execute that. And so you're executing that same code redundantly, an immense number of times. And when you run something in ZK, only one person has to execute it, and then everyone can make use of that. And so if you think about it, if instead of having 1,000 nodes all executing the same thing, you have 1,000 nodes each executing a different thing, and then exchanging that information. And so you basically scale, your compute scales with the number of devices instead of just only the security scaling with the number of devices. Because as you add more nodes to these other networks, you're really only increasing the security, you're not increasing the transaction rate at all.
I guess if I can just follow up on the question, the particular cost that I'm concerned about bringing down an increasing rate is the overhead of verifying certification relative to part of our design of our proof network includes this notion of aggregation where, because we have recursion in our proof system, we can verify a proof in another proof. You can actually take and have, I've proven A, B, C, and D, and then I can verify that I've done that, and I can produce a Merkle tree that just contains the statements A, B, C, and D, and that'll be all in one proof. And then I can verify that one proof, and then you can then use any of the facts that were verified. So what that means is that if you look at the thing, there's you add this additional complexity of walking this Merkle path, but you have less, you have to call the verifier less often. It turns out that as you add more proofs, the amortized cost of verification of the initial verification drops, but the cost of verifying the Merkle path goes up, and there's a sweet spot where we believe it gets down to about 20,000 gas to do a verify if you can aggregate multiple of them together and put them in as a batch.
I'm curious because there's so much research and development in proof system primitives, how much then that affects folks building tooling and platform, whether yourselves or others around that. Do you feel like that actually influences a lot then how you architect and build and develop product and things
I mean, clearly the research on proving systems has advanced rapidly over the last couple of years and continues to advance. And we're always basically trying to spend a lot of energy staying up to speed with the latest sort of new advancements. And we can, continue to try to move our platform always to whatever mechanism for proving is going to be the newest, fastest, best way to do it. It is slowing down a little bit, and like the new improvements are like oftentimes like the Minius stuff, for example, is really super awesome, and it will be much faster on custom hardware, but it's going to take a while for those things to get there. So it is slowing down a bit, but yeah, there's still room for. I mean, right now we're still getting like multiple times faster every quarter, like 2x, 5x, per quarter. At some point that's going to slow down, and the only way to move forward beyond that, because a lot of those are mostly just, some of that's new research, but a lot of that's just better engineering. At some point, we're going to hit that wall.
I guess more granularly, have there been times where it slows down how you guys develop product or like build things because you have to make it interchangeable in the back end for different systems?
Yeah, I mean, I think yes, but not as much as you would imagine, because we've done a lot of work to abstract. Like we actually have internally some compiling tools that help us translate our RISC-V circuit.
Right.
So if we make changes to the proof system, we can modify that to like. But yes, the answer is that in order to prepare for that sort of churn, you do have to engineer a little less. You have to engineer sort of defensively toward future changes a bit. Yeah.
Yeah, on that note of like proof systems, it seems like there's starting to be a whole class of proving systems with respect to recursion and IBCs that is better adapted to different computation that almost feels kind of like the way some databases were adopted for different types of like searches, lookups, and computations. So like, are you guys thinking about things like that, like how like a database query be more adept in IBC?
Yeah, I think there are a lot of places where specific use cases do want to directly relate to down to specific proof systems, especially for high performance. Like one of the real cases that's a real concrete example is ML inference. Like ML inference is very specialized, it's all linear algebra, and there are certain proof systems that can excel at that specific use case, where you may you may not want to use something that's very general purpose. And in terms of our product, we're focused very much on general purpose programmability use cases. But there are definitely cases where that it is relevant to get down all the way to that level, but not as often as you might imagine. It tends to be much less.
Thank you so much, Jerry, for that talk.